Okay, thank you, Dylan, for organizing this meeting and for the opportunity to speak at this conference. One thing I learned today is how to pronounce correctly Dylan, and my colleague Guillaume from Alfven, Guillaume but Sun John Dylan in X. Okay, so I would talk about regulations of Alfven eigenmode by microturbulence in fusion plasma today. This is the outlines, and this is my record of the earlier festival, 2007. I checked the property of the photo, and I recognize it's from 2007, and the resolution is only 1,000 lines at that time of this photo. You will see our progress of these resolutions from 2007 to today. Okay, so I would try to stay basic. I would first describe the energetic particle transport by multiple physical processes in burning plasma, and how do we develop an integrated simulation model to simulate this EP transport in burning plasma, and then an example of regulations of Alfven eigenmode by microturbulence in our recent simulations. Then if I have time, illustrate a few recent simulations of ether. Whoops. Am I stay on right? Okay. Did I move? Okay. All right. I think I passed a few slides. Okay. All right. So the motivation of this project is the need to study energetic particle confinement in fusion plasmas, because ignitions in ether rely on the self-heating by energetic particles, and so that is a critical issue for ether. The plasma confinement properties in the new ignition regimes of self-heating by alpha particle is one of the most uncertain issues when extrapolating from existing fusion device to ether. Somehow, can I remove this bar here? Good, thank you. All right, so this is the motivation for this SciTech project, scientific discovery through advanced computing. We were actually writing the proposal with Pat during the 2007 festival. Pat may not be able to recall that, more than 15 years ago. So this tries to develop integrated simulations of energetic particle turbulence by treating all relevant physical processes from micro to macro scale on an equal footings. So this project now in 15 years, including many energetic particle researchers in the US. We further developed gyrokinetic simulation code, GTC gyro, and several kinetic MHD codes, and more recently, more reduced models based on physics model, critical gradient model, resonant broadening quadlinear models, interpreted model KICS, and deep learning model FRNN and GTC. So this project established a new paradigm of the energetic particle studies using gyrokinetic turbulence simulation. This is needed for our predictive capabilities for energetic particle confinements in a burning plasma, because we need to study interactions of multiple kinetic MHD processes. And this is illustrated here. The energetic particles transport most of these driven by mesoscale, often instabilities, often eigenmode. However, those eigenmode and energetic particles would interact with microturbulence driven by thermoplasma, and this would thermoplasma transport and macroscopic MHD instability, potentially leading to the disruptions. So the energetic particle transport channel, even though most of it going through this, sometimes also MHD instabilities, but collisional effect and microturbulence could play important role. So I would illustrate how those interact through some basic physics of the Alfven eigenmode and EP transport. So let me go over a few basic items here. Now, Alfven eigenmode, unlike the microturbulence, very often are coherent that we can observe in the experiments. So it's kind of we dominated microturbulence regimes. The first principle studies of Alfven eigenmode involve the nonlinear saturation mechanism, how large amplitude Alfven eigenmode could be, given that Alfven eigenmode, how large energetic particle transport would be driven, and then some detailed properties, for example, intermittency and chirping. I will go over those status of the study. Those are first principle simulations require an theoretical insights and the verifications and of course experimental validations. So the goal is to provide physics basis of reduce energetic particle transport for real-time predictions and control in the burning plasma. Okay, and how do we predict confinement of fast ion in the ether? So this is the focus of U.S. Department of Energy Theory Performance Target this year and a IPPA joint activity. Now, first I focus on nonlinear physics because it's coherence. So the study very often begin with very simple wave-particle interaction, and that can involve the coherent wave-particle trapping when the frequency, the particle trapped by the wave omega bounce equals to linear growth rate, then the instability was saturated. That's the simplest pictures. Now, if you have many waves, of course, you can have the quasi-linear theory to describe the saturations because of the overlap of phase-space islands. The fast ions could have a flattened profile near the resonance, and so that lead to the saturations because you turn off the drive. This is a response of the EP to an ensemble of linear waves. Now, that response can also represent a damping to a particular wave, and so that is the resonance broadening theories that the wave can be damped by such diffusions of EP stochastic orbit because respond to an ensemble of linear waves. So those are the simple wave-particle interaction that has been studied extensively. Now, more recently, the wave-wave interactions got more attention, and that can involve the generations of zonal flow or zonal structures defined as proximal phase average potential occurrence, typically toroidal mole number n equals 0. They can transfer energy to damped mole and lead to nonlinear saturation or nonlinear modifications of equilibrium. And then you can have nonlinear mole couplings between different toroidal eigenmole. Finally, those couplings can be facilitated by a particle acting as a quasi-mole. So this is ion component scattering that TS studied before even I was in the field. Okay, so those are interactions that involve all the scale. You can see collisions comes in, microturbulence scattering of particle comes in, can change the wave particle interactions. Cross-scale coupling between Alfven and Alfven eigenmole can comes into those wave interactions. So important physics here, the cross-scale physics. Okay. Oops, those are not moving. Okay. Yeah, so we need to study the cross-scale coupling between microturbulence and MHD. And for microturbulence, we are familiar with turbulence gradients like earlier today lectures. Those can transfer energy to a damped locations. For Alfven eigenmole, typically it's localized in the radio, so this may not be that significant. Okay, so what is the status of our understanding? The key issue is what nonlinearity dominates saturations of Alfven eigenmole. This is studied in this gyrokinetic simulations showing the dependence of the saturation amplitude on the linear growth rate over the linear frequency. You can see initially it's quadratic, so that is a wave particle interaction with more important near marginalities. And then you see the linear dependence that is more like the wave-wave interactions due to, in this case, most of the zonal structures generations. So the question is how close to the marginality? This is a realistic D3D case, and you can see the transition occurred in about 3 or 4%. So it's pretty weak instabilities. For this D3D case, the simulations show that the linear growth rate over the frequency is about 8%. So we're in this wave-wave interaction regimes, even though the magnetic perturbation is very small, only about 0.1%. So I would think it's not in the stochastic kind of regime, but the wave-wave interaction would be important. One interesting finding in the last 10 years also is that zonal flow or zonal structure seems to dominate Alfven eigenmode saturations without cross-gas couplings between microturbulence and Alfven eigenmode. So this has been confirmed in many gyrocandid simulations, gyro GPC, GIMCO, and earlier kinetic MHD simulations, MEGA, CAEFL. So you can see from this GPC simulations in D3D discharge, without zonal flow, the saturation amplitude would be 4 times higher than the case with the zonal flow. And then multiple interactions comes in, I will discuss later, but not that significant for D3D. Okay, so now given such a AE turbulence, what transport level you could expect? So this would require some basic understandings of the transport, because many students here, I will describe how we get to this transport. So the transport is due to the breaking of the adiabatic imbalance in antisymmetric tokamak. And that need to look at the 3 adiabatic imbalance, and due to the 3 periodic motions. One is the cyclotron motion due to cyclotron frequencies, and then the guiding center motions along the field line give you this bounce frequency, and then the guiding center drip across the field line give you this precessional frequency. Okay, so given such 3 frequencies, any resonance or nonlinear effect can break those linear frequency related adiabatic imbalance. Okay, so they involve the linear resonance. If the frequency match one of those, you would break those adiabatic imbalance. Typical Alfven eigenmode has frequency below cyclotron frequency, so we always have magnetic moment mu as constant. So you can have a 2-dimensional resonance from the combinations of precessional frequency and bounce frequency. Okay. If the frequency is so low, like the magnetic perturbations, you can have the ripple loss due to the drip bounce resonance. Now, sometimes we have the even lower frequencies that preserve the bounce motions adiabatic invariance. Then you can have second invariance, parallel or longitudinal adiabatic invariance. Then this reduces everything into 1D, described by this toroidal angle momentum P zeta and zeta. And that is a 1D model very often in the theory, gives a simple 1D dynamic. However, it's important to point out P zeta here is almost like radial coordinate, and that leads to very interesting physics I will describe. Okay, beyond those nonlinear or linear resonance that is to the transport, you can also have nonlinear scatterings because of these trajectories affected by the wave that lead to the stochastic orbit. Those linear resonance calculate the linear orbit without the perturbation by the wave. And then you can have collisions that break the constant motions that also lead to the transport, and collision can also damage zonal flow. Okay. Now, recently we found, more importantly, energetic particle scattering by the microturbulence because of this P zeta is a radial coordinate. And so the E cross B drip actually is very effective to break this P zeta rather than collisions, because collision does not change much of the P zeta. Okay, so that has been reported earlier, this diffusions of the E cross or the energetic particle by microturbulence. And they can destroy the fast ion phase-space structures, for example, incorporated in the reduced RBQ model. It can also damage the zonal flow because you generate a radial zonal structures by AE, and those can be damaged by microturbulence, E cross B drip. So this is kind of interesting because usually within microturbulence generate zonal flow, but if the zonal flow is mostly generated by Alfven eigenmode, so microturbulence can damage the zonal flow. So all these studies, we try to extrapolate to ethers, and that involve multiple end couplings. I will illustrate later on recent simulations. It could be more important in ether than current tokamak like D3D. The scattering by microturbulence would become weaker, decrease as 1 over time of temperature T. However, the collisions decrease even faster. So eventually, the microturbulence could be more important than collisions. And even in the D3D, we found the collision is not important compared to microturbulence. Okay, so now what is the current status given this background about the EP transport? How do we understand the current simulations? First of all, the most important conclusions I would lay down is that there is no steady state EP transport in any current simulations treating just Alfven eigenmode. And that's quite surprising because that is not consistent with experiment. how do we lead to that conclusion? First of all, we have a very large EP transport in the Hawk-Q simulations with zonal flow, and that was illustrated by these gyro simulations. And the fast ion diffusivities would be unbounded if the Alfven eigenmode growth rate is larger than ITG. So that rely on ITG producing zonal flow, which saturated Alfven eigenmode. The more recent simulation by Jin, shown in this recent Nature Physics paper, the ITG can be suppressed by TAE. The paper does not say how big is the Alfven eigenmode amplitude or transport. In the conference discussions, it seems that the diffusivity would be very big, and that number would not allow any heating by fast ion, because typical fast ion diffusivity is 1 meter square per second. Okay, now how about the global simulation? In the global simulations, we see that the EP transfer has a huge burst at the saturations and then drop to zero quickly, basically from all the geokinetic simulation code that we reviewed in the last year in the SciTech ISAT project. Shown here is orbit-side simulation. You have a huge burst and then drop to zero within 0.1 milliseconds, and that's very similar to all the code. Okay. For the global kinetic MSD simulation, is also similar by all this code that we reviewed. Okay, now how about collisions? We found that without zonal flow effect, collisions have some effect on the Alfven eigenmode saturations and EP transport. And you can see the EP transport will increase with collisions. However, when we have zonal flow, then the zonal flow effect is more important than collisions, and we don't see effect of collisions in the tokamak like D3D. Okay, now from all these results, we see that there is no steady state transport observed in experiments unless you have additional dissipation. And in the kinetic MHD simulations, such dissipation usually is by artificially large resitivities or viscosity. Recently we found that quasi-steady state transport can be maintained by a microturbulence effect. Chris?
It's an overview with that essentially quasi.
It is the particle trapped in the phase space forming the islands, and there is no effective way for the move particle between different islands, basically, because of weak instability. ITG, you have a larger gamma over omega r, so the particle can move across the whole phase space. That is basically what we understand. And turbulence, the collision can have effect because this showing those effect the phase space islands. Not global fractioning, because only a very few particles participate in resonance because of the sharp resonance. Gamma over omega r is very small, usually it's more than 10%. All right. Now, how about intermittency and choking? They are related. So I would describe a bit about the intermittency here. Global kinetic MHD code does observe some kind of intermittency by mega and Far3D. You would ask what led to this second burst and then repetitive burst. Now, in the Far3D simulations, it's a gyro fluid model, so it's understandable because it would not allow phase space islands. It did show all the phase space islands. So you have a burst and then zonal flow saturate AE, and then you don't have transport, and then later on second burst because AE all the fluctuations loaded them those zonal flow. So that's easy to understand. Now, mega have some kind of repetitive bursting, and that usually rely on the source. You have to have a source to replace the particles that are trapped by phase space islands. However, the source has a very long time scale in experiments. Typically, it's at least 50 milliseconds in D3D. In E2, it will be much longer. Time scale is very long, but you can see that the token is very fast, intermittency on the order of sub-millisecond scale. So you cannot rely on the source to get the choking or the intermittency. Now, the recent observations of choking or intermittency is more pronounced in negative triangularities, provide some interesting background here. The argument here is that negative triangularity has a weaker microturbulence, so that's good for confinement, and so it has a less damping to the Alfven eigenmode. So if you compare positive triangularities and negative triangularity for these two cases, dominated by TAE or RSAE, toroidal Alfven eigenmode, reversible Alfven eigenmode, they are more pronounced choking intermittency in the negative triangularities because the damping by microturbulence is weaker. And so this is stronger. So kind of in a nonlinear dynamic language, this is more already in the kind of stochastic regime. This is more like in the limit cycle regime. In recent simulations from DTC, we see kind of similar interesting bursting here. In these simulations, we have the microturbulence as background, which drives very small fast ion transport. And then the Alfven eigenmode growth and drive a large zonal flow, which saturates the Alfven eigenmode. And then at that point, you have a large diffusivity of the fast ions similar to experimental levels. And then the zonal flow damp the Alfven eigenmode and reduce the transport. But eventually, the zonal flow lower to the lower level, the children rate is roughly the same as Alfven eigenmode growth rate, and that allows the Alfven eigenmode growth again and drive large transport again. In this process, the microturbulence you can see from these electron density perturbations does not change much. So this reproduce some kind of feature of this repetitive bursting or intermittency. Now this intermittency often is related to the chirping frequency change in the Alfven eigenmode. So how do we describe or understand this chirping? Chirping, the frequency change you can see from here, these three observations. The frequency of this BAE of beta-induced Alfven eigenmode chirps down within about 0.3 milliseconds. And this pattern repeated within 1 millisecond for a very long time. Now the source terms would need about 50 milliseconds, so it's the whole measurement here, but there are hundreds of chirping inside this window. So how the nonlinear dynamics lead to these phase-based structures? The standard model is 1D perturbative theories, the so-called BMB models based on separations of scale, assuming that the phase-based item rotate very fast, and then you have a dissipation on a longer time scale. So those are separations of frequency, and that lead to the frequency pitch forkings because of the phase-based Kramer and Hall stripping away slowly, changing the frequency. But it cannot produce a repetitive chirping or oscillation of amplitude until you have a source of dissipations that destroy this Kramer and Hall. Now we observe that very often the two-dimensional physics comes in. I mentioned two things before. One is the frequency, the resonance can be more than just one dimension. Precessional frequency. It can have a combination of drip bounds, so it's intrinsically two dimensions in that 2 degrees of freedoms in that drip bounds resonance. The second interesting physics is this physics of the P zeta. I mean, it's present here. In 1D theories, everything depends on this one-dimensional model. Zeta is like X, P zeta is like V in the 1D model. And so in a one-dimensional nonlinear dynamical model, the wave amplitude would be a function of the zeta only, and that represented by this K space, n zeta, and the frequency omega. However, in the tokamak, even if I have only one-dimensional resonance, P zeta is almost like radial coordinate. And so the wave amplitude would depend on the radial coordinate. So now the P zeta comes in the wave amplitude. This does not happen in the one-dimensional dynamical model like BMB model because P zeta appears as velocity v, right? The mole amplitude cannot depend on velocity v. But now you have a two-dimensional problem here. P zeta enter to the mole amplitude, and that lead to the phase-space structures appear in the real space, and that phase-space islands would be limited by the mole width in the real space. And so the dynamics of that phase-space Kramer and Hall is intrinsically two-dimensional problems, not just in zeta, but also in P zeta. Okay. And so that led to this interesting the chirping and oscillations of wave amplitude kind of on the sub-millisecond time scale, similar to the experimental observations that would not be able to reproduce from one-dimensional nonlinear model for the amplitude oscillations and repetitive frequency chirping. So that's the Chopin physics. All right, so given those backgrounds, I would argue that we need a integrated simulations to treat interaction between different scales, from micro to meso to macroscopic scale. And so I would describe how we do that in an integrated simulation. This is the 2011 festival that I took the pictures, and now the resolutions increased to 2,000 lines of these pictures in 4 years. So that was quite good improvement. Sorry, I messed up with my upper left.
Oh. Sometimes not too much technology is a good thing.
Okay, good. All right, so that's the second part about the integrated simulations. I would probably need to move faster. Oh, okay. So then I would move very fast. Okay, I will just describe how the difficulty and how we overcome the difficulties. Typical simulations in the microscopic scale is now kind of standard and it's easy to do in the microturbulence. When we try to do the mesoscale or MSD simulations, there's a problem because of these cancellations of the inductive electric field and the electrostatic electric field. In the IDMSD, the E parallel would be almost zero. And we try to, in the gigantic simulation, we try to calculate both terms and then try to cancel them out to give the E parallel, and that's a very small number. So this is a critical problem of cancellation that we need to overcome if you want to calculate the potential and then calculate the electric field. And then to give the problem even more difficult level here, very often we don't calculate this quantity because you need to take a time derivative. And so we often define canonical momentum as independent variables. And then the Poisson equation becomes this form, adding these two big terms, this big term here, omega p squared over c squared, which is much bigger than this term here by this order. And then we need to calculate the data A parallel very accurately from these operators. And so that leads to calculations of the second order quantities from zero to order quantity. And this is infamous problems of cancellation problems. So we don't want to do this, and we can learn from MSD simulations. You don't calculate potential to calculate electric field. You actually calculate electric field. You calculate the second order quantity accurately, and then you calculate the lowest order quantity. So that this is the model that we developed. We separate the electron response into adiabatic and non-adiabatic, and then the parallel electric field also adiabatic and non-adiabatic. The adiabatic just very simple force balance of electron, and then the non-adiabatic response calculated by the Goodrich scheme, and then you correct the E parallel from non-adiabatic response. So that we cover all the ITG to KVM transitions. Now the price you pay is that you cannot calculate the thermals. In order to do the thermals, now we don't do the expansions. We separate the effective potential into the adiabatic and non-adiabatic part, and then we calculate separately. And that is similar to the scheme called sympathetic scheme that calculates those E parallel from adiabatic and non-adiabatic response. Okay, so given all those models, now we construct this code that can calculate all those microturbulence, Alfven eigenmode, MHD. I would skip those. Now, those still very expensive to simulate, so we need to use the most powerful computers, and so we have to spend lots of time working with the computational scientists to optimize the code on the GPU using a multi-level parallelizations, which lead to this scaling up to the whole machine of the GPU computer in order to do the simulations I'm going to show you in the next slide. Okay, so I'm going to now move to the third here. The regulations of Alfven eigenmode that use the most powerful computer. We spend about 1% of the summit time for this study, so that you can imagine how much time we spend on this project alone. So this project started from this verifications of the gigantic simulations of the Alfven eigenmode and MSD mode. And this is a verification of the Roche Alfven eigenmode by many gigantic code and the MSD code. VM reported last week about the verifications of kin simulations by geokinetic and the kinetic MHD flow. So now we extend this linear simulations to nonlinear regimes. And this is what we found in that particular D3D experiments. There is a strong RSAE, about 8% of gamma over omega r in that experiment. But at the same time, there's a strong ITG in the experiments. ITG has a dominant mole number 16 RSAE n equals 4. And you can see that the electrostatic potential is dominated by the RSAE, and then the density perturbation dominated by the ITG. Okay, so they coexist in the simulation treating both of them. The ITG actually is most of the contributed growth rate contributed by the electrons response, and they interact with each other. The ITG has a strong effect on RSAE because they can scatter the energetic particle orbit, destroy the phase-space islands. They can dim the zonal flow and zonal structure generated by the Alfven eigenmode. And they can be a direct mode coupling between AE and the Alfven eigenmode calculated recently by Lu Chen. Okay, on the other hand, we found small effect of RSAE on ITG in these experiments. So now let me illustrate how this ITG affect the RSAE. We first have a simulation of RSAE only. So we keep the total mole number from 0 to 10, where the RSAE has growth rate larger than ITG. And you can see that RSAE increase to amplitude to a large level, drive a large zonal flow. And then the zonal flow saturates the RSAE, but then RSAE amplitude drops to a very low level. The fast ion diffusivities saturate at very high levels, several times higher than experimental values, and then quickly drop to zeros within 0.1 milliseconds. Okay, and then the zonal flow stay there. There's no second burst of the transport. So this is inconsistent with the experiments. Okay, there's no quasi-static state EP transport. Now, in the next simulation, we include the ITG turbulence by keeping total mole number from 0 to 25. And now you can see that we first allow the ITG to grow, and you have the background ITG turbulence, which drive a very small fast ion diffusivities. And then the RSAE goes to large amplitudes, and that generates the zonal flow, which saturates the RSAE. Now, the fast ion diffusivity is large, about 1.5 meters square per second at saturation similar to the experimental value. And then it drops to low level quickly, but then the zonal flow is slowly dimmed by the microturbulence until the Shearing rate is on the order of RSAE growth rate. Then that allows the RSAE growth again and drive the fast ion transport again. And then that also led to the increase of zonal flow, and that saturates the RSAE again. So this process repeats itself, give you the repetitive burstings of the transport of EP, give you a quasi-static state transport. And that is consistent with experiments. Now, we measure the mole amplitude and compare with the experiments. So shown here is the RSAE amplitude measured by the ECE, the electron cyclotron emissions, radial profile, and the absolute values with a large arrow bar. The black line is from the GTC simulation. It's quite amazing. It matches exactly in terms of shape and amplitude. And this is for the first time that geokinetic simulation is able to match experimental measurements of the AE amplitude. Before that has not been done at all. Okay, the electron density perturbations is dominated by high K, high N components that is ITG, and the low K of RSAE has much weaker density perturbations. The amplitude about 0.5% agree quite well with the BS measurements. Okay. The average fast ion diffusivities is about factor of 2.5 within the experimental measurements. There are other PAE in the outer edge that we did not simulate that may contribute to the difference. But this is the first time that the geokinetic simulations were able to recover the experimental RSAE measurements. So this was reported last month in this paper. All right, and this simulation again is the largest electromagnetic geokinetic simulations so far covering different scale. All right, now we go back to 2007. I guess my time is up. I probably skip the last part of the simulations of ether.
Can discuss it on the portions.
Yes. All right. Okay. Thank you very much.
Time for questions.
I guess, Mr. Pratt, I mean, I'd be interested to hear about your thing specifically. Does anything, I guess just to kind of set up that last bit, what, if anything, you looked at when you go to either, like quarter man, smaller star, you have to be a denser spectrum, what?
Okay, a few items maybe I can highlight here. So we are now focusing on ether simulations at the ITPA here, and we simulate two baseline case and steady state case of ether and matching D3D case. So those are selected by the ether IO and the D3D experimental list. And we found that response reported by Guillaume last week in the baseline, and AE appear in all the cases. Microturbulence dominated by trapped electron mode in ethers baseline, but steady state is ITG. So what we found, I think two things. One is the response in the baseline case is not that severe. It reduced very small fast ion gradients as reported by Guillaume. One interesting physics Guillaume found is this phase-space Crum and Hall driven the response is affected by the zonal flow. And that go back to our earlier comments. The phase-space structures in this resonance could be in the real space, p zeta and zeta. P zeta is precise radial functions. And so now you have an interesting new physics of zonal flow. Zonal flow affect phase-space Crum and Hall. In the ITG, you don't see that because Crum and Hall is in the velocity space. And so the zonal flow would not have effect on that. But now the Crum and Hall is real space structure, and zonal flow can shear apart the phase-space Crum and Hall or trap the coherence of phase-space structure. So that's very interesting. But for ether, this is not a big concern for the baseline case. Let me go to the another case, the steady state. This seems to be a bit of a concern for the steady state Alfven eigenmodes. These simulations include all the unstable Alfven eigenmode, about 30 modes. It's very large spectrums, and they are saturated by zonal flow. We do not include the microturbulence in this case. And you can see there's a big burst of the transport for the MBI and for alpha particle. And the amplitude reach about 100 meters square per second. This cannot be allowed in ether because otherwise you won't have any heating by alpha particle or MBI. Fortunately, this burst is very short time scale, about 0.2 milliseconds. So the effect on the redistributions of the fast ion profile is not that severe. But the simulation is not complete because this is just Alfven eigenmode itself. There's no MSD mode, no microturbulence. Those would couple to this and change these pictures. So that's the second physics we learned so far in the ether simulations. This is very expensive simulations of ether. Another, the third one is microturbulence, and this I thought is interesting. For the baseline case, ether and D3D match very well. They both dominated by TM. The mode number is big, has big difference. D3D has n number up to about 40, 50. Ether up to 400, almost factor of 8 differences. So this is huge simulation with n number of 400 in the ether. The largest simulation so far in the ether simulation. They have very strong growth rate. When we look at the nonlinear simulation results, they drive transport actually is a good news in the very well Jeroboam regime. So D3D has a chi-I, chi-E on the order of 2 meters square per second. Ether also have similar order, 2 meters square per second. Now, for some reason, this D3D has a very large particle diffusivity. Ether has very small. It's just passive to the trapped electron mode in this case. So the good news is heat diffusivity in ether is not bad. It's basically Jeroboam scaling from D3D. So this extrapolation is reliable for microturbulence. What is not known is Alfven eigenmode. How large the transport will be driven by Alfven eigenmode, we don't know. We have not finished this project yet.
Yeah, it's probably traveling.
That's true. Yes. This has not been properly normalized yet.
Comment about the spherical tokamaks. Spherical tokamaks are very special as to Alfven eigenmodes. Indeed, I published last year a nuclear fusion with my colleague Fabio Satin from Consorcio RFX paper showing that the magnetic moment is not well conserved at all in spherical tokamaks.
Right.
And the consequence is that the Alfvenic resonance is intermittent, okay? And so it's hard to excite the Alfven eigenmodes. And so in some sense, the bad news about the non-conservation of the magnetic moment comes with good news. The bad news is that since U is not, the magnetic moment is not well conserved, we cannot use gyrokinetics or guiding center calculation as people are used to.
Right. Now, I would comment that the magnetic moment would be conserved for some phase-space regions in the fast ion in the NSPX, like in parameter.
Yes,
Some space had pretty poor conservations of mu. In terms of Alfven eigenmode, it's actually much more common in the ST to have the Alfven eigenmode than typical tokamak. So I don't know how is this related between the conservations of magnetic moments and the excitations of Alfven eigenmode. If you look at NSPXU, it has huge Alfven eigenmode activity compared to a typical similar tokamak, regular tokamak. So I think Alfven eigenmode is a big concern for ST. In the current ST machine, use neutral beam that is tangential injections. So most particles are passing particle mu are well conserved. Now you have a perpendicular injection, the mu would be less conserved because they are trapped particles, they are in the low field side. And this
right, the special localization is more the outer part.
Yes,
of the
exactly.
machine, so you're less likely to lose your alpha particles of the whole.
I'm not so sure for alpha particle. For neutral beam, because you have the tangential injection, they are well confined. But alpha particle is isotropic. So most of alpha particle will be trapped in low field side. And as you commented, the mu may not even be conserved. Whether the particle orbit would be well confined, that's one thing. Even if they are well confined, they are trapped particles in the low field side. It's a huge free energy. So I think they're going to drive a lot of Alfven eigenmode by alpha particle in the low field side by the trapped alpha. It has not been studied. We just now try to study this physics ST. Ted, you have?
Is there a bottom line of feedback loops? In other words, you would have a picture of, you have two populations of turbulence now and zonal structures.
Right.
One would like some kind of picture of the possible states, right, and feedback.
Right. I guess the transport by the Alfven eigenmode led to a degradations of the heating, and that will change the thermal plasma pressure gradients. So that will change microturbulence. Right, they could be such a loop here, nonlinear interactions loop, but they happen on a longer time scale.
Yeah.
The one I described very short time scale, sub-millisecond.
And what is presumably
Yes, but it's not dominant. The most effect still coming from the zonal flow.
still?
Yes.
So I mean, can the A produce what amounts to a unit shift state in the thermals? I mean, you just kill the thermal turbulence by the zonal flow, and it's, in other words,
Right.
so you would have one state of
Yes.
of AE dominated, one state of thermal dominated.
Well, I think you may kind of consider this similar to a image shift. You have a zonal flow and then suppress everything to be almost zero, right? However, there's a difference here. In the ITG case, the zonal flow is the only one that lead to the suppression of microturbulence near marginality.
Right.
That's image shift. Alfven eigenmode, if you're near marginal, there's another physics wave particle interactions that would saturate the wave even without zonal flow. So I'm not so sure whether that in that regime the zonal flow dominates.
And what about the effect of the scattering of the orbits on by the microturbulence on the response of the AE?
I mean, the response of fast ion to AE.
Yeah, exactly.
So there are two physics here. One is the scattering by turbulence to fast ion would change the wave particle resonance interaction,
Right.
obviously, right? But more interestingly, they can scatter the fast ion between islands. Now, AE has separate small islands and get it to the localized transport, so you don't have global transport. But now the E-cross feature can scatter them across different islands, popping the islands into the global transport. So I think that's very interesting. Physics has not been explored very well. There's another scattering that them the zonal structure that is zonal flow is not just
That shows this
we haven't studied that detail yet. But in terms of scattering, there's another physics that very interesting that is special to ether. The zonal structure or zonal flow can be generated by both fast ion and thermal plasma. Now, the fast ion zonal structure would be less sensitive to the microturbulence because the temperature increase for the alpha particle. However, the zonal structure of the thermal plasma would be destroyed by microturbulence, and that would not depend on the temperature ratio between alpha particle and thermal plasma. So when we scale to the ether, that physics becomes more important. And so all this has not been studied before. Chris?
Well, just on something you were asked about that Mazzy paper that came out, I believe, well, basically that any so that means that I think that the heating generates a little bit for that stuff. You have that's what out there in particles and
Yes, in principle, any zonal flow generated by any mode would reduce microturbulence transport. The question is how big the zonal flow you need and how big the amplitude of Alfven eigenmode or fast ion transport level it would need to produce enough zonal flow to suppress ITG.
I think that's kind of what they.
The paper does not say anything about the TAE, the amplitude, the fast ion transport. But during the TTF invited talk, Eric asked these questions about the diffusivity of fast ion, and I asked the same questions. They also say it's about 60 meters square per second. I don't know if this is exact quoted maybe incorrectly, but this number would not be tolerated in any machine. If this number in jet, you can calculate, probably there's no heating. But
Back a lot of cluster. 60 meters square per second.
I mean, given the jet parameters, if your fast ion diffusivity is this large, you won't have the PI you would have in jet. There's no heating. Okay, and that's one thing. The more fundamentally, the Eric Fox and Ron was showed in this cell simulation. The first two simulations TAE cannot saturate. You just go to infinite amplitude. So we don't know how the TAE is saturated in this paper. I did the paper on the way here. I did not find any discussion. What is the TAE dynamic? How they saturate? What is the amplitude? So I don't know for those details. But given that discussion, this seems to be extremely large, and that would be impossible in ether to have this kind of transport. It still has the heating. Typically, we have in T3D on order 1 meter square per second. I will not think that has a larger diffusivity.
But there will be before some kind of self-regulation, because as you say, at this level of transport, they have.
Right.
For that, what kind of
Yes, yes. So again, the first two in this simulation that was discussed very detailed in this paper that they cannot saturate basically, unless you have zonal flow from microturbulence. But the global code does saturate all the global simulations has the saturation. And the problem I was shown here, like this orbit by code simulation, is very large amplitude at the beginning, at the saturation, and then drop to almost zero quickly within 0.1 millisecond. So that's a very common feature of all these global gel interval. So it won't have a large sustained transport from global core, but positive core give you this unbounded transport in the gel simulation. So this is not clear to me in the positive simulation what is the AE saturation mechanism and how big is AE amplitude, and they can be compared to the experiment. For example, our simulation is showing delta B over B is 0.1%. Whether this is observed in that simulation, and how large is the diffusivity of fast ion, because that experiment has a modeling of transport. You have a diffusivity of the fast ion, how they compare with the modeling of the fast ion diffusivity. So maybe someone has information, but I couldn't find those information from the paper.
But I think in Mazzi's case, the TA is separate, it is linearly stable, so probably you use some kind of separate.
Right. So then the question is how large is the fast ion transport can be driven?
Expanded by turbulence, so that's why you want FW quite large. But I think it saturates because you start from a state where it's stable.
So what amplitude of the AE could drive?
I don't know. Is there questions? I have a language. Thank you again.